Good morning, I'm Mr. Precella, and today I want to talk a little bit about the derivative from my Math 1325 class. Notice I have the graph of a function y equals f of x drawn, and I have the x-axis and the y-axis drawn. And let me label them. And I have a curve, just a generic curve y equals f of x. What I'm about to do is true in any quadrant, but just to stop those x and y axes from passing through the graph so much, I'll draw most of this curve that I'm going to be looking at in the first quadrant. And I'm going to have a initial starting value of x labeled on the x-axis, just a general arbitrary value on the x-axis. Let's suppose I move h units to the right. That's h units. Then this new number here on the x-axis, it's whatever that number is plus h. And let's suppose we go to the point that has x and x plus h as its x coordinates. If we draw the line connecting those 2 points, that line is called a secant line. A secant line connects any 2 points on the graph of a curve. And that is the secant line, not to be confused with the secant function in a trigonometry class. That is the secant line. If I wanted to know, on general, on the average, how much is the function changing as I move from x to x plus h, that's referred to as the average rate of change. The average rate of change it's just the slope of that line. We know the ordered pair. This is x, f of x. This point here is x plus h, f of x plus h. And we could just find the slope of the line using our slope formula. Remember, the slope formula is y2 minus y1. So f of x plus h minus f of x all over x2 minus x1, so x plus h minus x. And I could clean that up a little bit. I didn't need such a long line. I'll write it here. Just f of x plus h minus f of x all over h. There's the average rate of change. Basically, this numerator is giving us the change. There's f of x, and there's the terminal y value, f of x plus h. The average rate of change is giving us that difference in the y values divided by the difference in the x values. Exactly what we expect from an average rate of change. What we're concerned with here in this course is not average rates of change. We know how to find an average rate of change. It's just the slope of the line connecting the 2 points. What we want is the instantaneous rate of change. How can I determine how fast the function's y coordinates are changing at that one moment in time, rather than looking at some big interval of time? How quickly are they changing at that one spot? In order to determine the rate of change at that one spot, what I'm going to do is I'm going to start shrinking. I'm going to start moving this point in so that it's closer to that spot that I'm concerned with. Well, if I were going to move this point in closer to the initial point, then h would have to be getting smaller as well. Remember, h is the distance between the starting x value and the stopping x value. So let's start shrinking in h. Let's let h get smaller and smaller until our second point Our second point, it's so close, I'll make it look like it's not, that they're, that they're not, but, that they're two distinct points. But let's pretend we shrink it in so much that that second point is so close to that first point that it looks like it's the same point. Draw that secant line. If you shrink down that interval, so it starts at x and it goes to x plus h, that interval is so short that the rate of change of this new orange secant line, should be approximately the rate of change of the function at one specific time. That orange secant line that's not showing very well, I'm going to make it red. There, I think that's better. This red line, to the naked eye, it would look like that red line is touching that curve at one and only one point. That is referred to as a tangent line. You would have seen or discussed the concept of tangent lines in relation to circles in your high school geometry class. Now we're extending that concept. To the naked eye, it looks like the curve is touching the graph at one and only one point. And in order to get an idea of what that curve looks like, choose a second point that's right beside the initial point. Draw the line connecting those 2 points. To the naked eye, it'll look like the line is touching the curve in that one and only one spot. So, for the instantaneous rate of change, to derive a formula for the instantaneous rate of change, the rate at which the function is changing at that one specific time, we need the slope of that line right there, that red line. So what do we do to the average rate of change formula? Here's the average rate of change formula. In order to move that second point in closer to the first point, we had to let h go to 0. H is the distance from x to x plus h. When we shrank down h, we got a second point that gave us this new tangent line right there. So we're going to let h go to 0. That means we're looking at the limit as h goes to 0 of the average rate of change formula. That's f of x plus h minus f of x all over h. We took the average rate of change formula, we let h go to 0, that then gave us the instantaneous rate of change. That's the rate of change at one specific point in time. In this function, defined by the limit as h goes to 0 of f of x plus h minus f of x all over h, is called the derivative. Let me write that. The derivative is the function defined by f, notice this notation, f prime of x, that little accent mark, you're going to be seeing a lot of that in this course. So limit as h goes to 0 of f of x plus h minus f of x all divided by h. If this limit exists, remember we saw plenty of problems where the limit didn't exist, so it wasn't a number. If this limit exists. And some applications that we'll be seeing in the following homework assignment, some applications for the limit, for the derivative. The first one is that slope of the tangent line. If you need to find the slope of the tangent line, and really anything involving rates of change, the instantaneous rate of change. And one thing that I think of is velocity. If you look up the word velocity in the dictionary, it's going to say the rate of change of the object, of the position of some object. And so rate of change, that's the derivative. So the velocity, that would be an example of an application where we would use the derivative. The rate of change of cost, profit, revenue, those are referred to as marginals. We saw the marginal cost in Math 1324 for linear functions, but now we're going to extend that concept. I'll say, so to functions that aren't necessarily linear, I'll say marginals, and that's for cost, profit, revenue, and let's see, anything that we can, we'll see additional applications as we go through this, but right off the top of my head, that's slopes of tangent lines, the velocity, and marginals are three applications that come to my head when I think of derivatives. We found a lot of limits in the previous homework assignment when we were discussing that unit over limits and continuity, but I think instead of using this limit definition of derivative, since this is for this is a business calculus course, I think what I'm going to do is I'm going to state some derivative rules, and we'll start using those instead of the limit definition of derivative. So derivative rules. And I'll tell you right now, what we're about to start will not go away. The rest of the semester, every class will either find derivatives, or when we're not finding derivatives towards the end of the class, they're going to start giving us the derivative, and we're going to have to start going backwards to the original function, which means we're finding anti-derivatives. But either way, derivatives will not go away. So get used to that. I have some notation. I suppose before I state my derivative rules, I need to mention some special notation that I use for derivatives. Given the function y equals f of x, the following represent the derivative. The following notations represent the derivative. And I'll say the derivative with respect to x. The notations that I'm writing are assuming that the independent variable is x. So I'll say the derivative with respect to x. This is a calculus of a single variable course, so in most cases we'll be differentiating with respect to x, or whatever the indicated variable is. Towards the end of the semester, when we get to implicit differentiation, related rates, it'll be more significant, the variable with which we're differentiating. But for the time being, it'll all be with respect to x. So f prime is a notation that I've already mentioned. Another one would just be to take y and put the prime on it. I like that notation. I'm a minimalist. The less notation, the better, in my opinion. And here's a notation that I'll be using when we lot, as I'm stating the derivative rules. A capital D sub x of y, the derivative of y with respect to x, or the derivative of f of x with respect to x, or dy dx. Here's another notation. Let's see. And that's read as dy dx, not dy divided by dx. And on my math lab you might see this notation. I'm not too fond of it. the derivative of f of x with respect to x, and, well, I think those are the most common notations. So any of these notations, if you see D's, you're not sure what the notation's representing, but if you see D's in it, what should you think? Derivative, okay. If you see primes, derivative. So if you're given a function at this point and you're not really sure what to do with it, then many times the thing to do is start finding the derivative of it. And now I'm going to find some derivative rules. So I'm writing my derivative rules now. Given y equals f of x, the first derivative rule. The derivative with respect to x of a constant is 0. And I think I'll list the derivative rules and then we'll look at examples. The next one, the derivative with respect to x, just of x, is 1. The derivative of just x is the number 1, and I'm going to generalize that. Suppose we had a coefficient sitting there in front of x. Here's the generalized version. If you have the derivative, if you're trying to find the derivative with respect to x of a number times x, that derivative is just the number. Suppose we want the derivative with respect to x of x to the n. This rule that I'm stating right now is frequently called the power rule for differentiation. You take that exponent, n, move it down in front of x, and subtract 1 to get the new exponent. So n times x to the n minus 1. And if we wanted to generalize that, suppose there was a coefficient times x to the n. You take the n, you multiply it by the coefficient, so n times c, subtract 1 to get the new exponent. And that power rule is going to be extremely important. The final rule, the derivative rule that I'm going to state right now, the derivative with respect to x of f of x, suppose you have a sum or difference, plus or minus g of x. If you're differentiating a sum or difference, all you do is differentiate each term individually. Now that's not going to be true when we're differentiating a product, but for a sum or difference, to find the derivative of a sum or difference, you just differentiate each of the terms individually. And I have some examples. Let me find them. I have some examples right here that I want to do. And let's see, I think let me get myself a piece of paper to use. Okay, and there. And it might be a good idea. I'm going to fold my derivative rules right there for the moment so we can be looking at them. Or at least so I can be pointing at them. So here we go. They want us to find f prime of x if f of x is equal to negative 1. F of x is negative 1. Looking at the first derivative rule, the derivative of a constant is 0. So right here in this blank, we would write the number 0. Now before we go on, y equals negative 1. How much is that y value going to be changing? Think about the rate of change. As you change your x values, by how much is that y value changing? It's never going to change, is it? The derivative gives us the rate of change of the function. Since that function's y values are never changing, the derivative is 0. y equals -1, that's a horizontal line. If you were to draw that graph, y equals -1 is a horizontal line passing through -1 right there. Are those y values ever changing? No. What's the slope of that line? The slope of a horizontal line, there it is, 0, which agrees with our concept of the slope of the tangent line. Number 2. Let me get a... Okay. We're told to find f prime of t, if f of t, so in this case instead of an x we have a t, and so this is number 2. F of t is equal to 9t cubed minus 7t plus 3. They want us to find f prime at t. F prime at t. Remember I said to differentiate a sum or difference, you just differentiate each term individually. So we're going to have to first of all differentiate 9t cubed. 9, well in this case x, or t cubed. If you have a number times a variable to a power, use the power rule. You take the exponent times the coefficient. 3 times 9 is 27. You subtract 1 to get the new exponent. 3 minus 1 gives me a new exponent of 2. Minus. Now we differentiate 7t. That's the line right above it, right here. A number times a variable. If you're differentiating a number times a variable, the derivative is just that number. So a minus 7. What about the derivative of plus 3? The derivative of a constant, is 0. So plus 0, 27t squared minus 7 would be my final answer. Get used to what we just did. That exponent times the coefficient to give you the new coefficient, subtract 1 to get the new power. We're going to be doing that a lot, that power rule, and it's not going to go away. It's going to follow us. We'll get more derivative rules as we move through the course, but they're all going to build off of these first 4 derivative rules I've written right there. So you'll want to commit those derivative rules to memory. And let's see, where was that? So right here, number 2, we said that's 27t squared minus 7. Here's number 3. Let me write it down. They want us to find y prime for y equals 2x to the negative 7 minus 9x to the negative 1. Let me put my derivative rules back there. They want us to find y prime. So y prime, it's back to that power rule, a coefficient times x to the n power. You take the exponent times the coefficient. Negative 7 times 2 gives us a negative 14. X. What do we do to get the new exponent on here? Negative 7 minus 1, that gives me a negative 8. Negative 7 times 2 gave me the negative 14. Negative 7 minus 1 gave me a new exponent of negative 8. Move on to the next term. Negative 1 times negative 9, that gives me a positive 9x. What am I going to have as the new exponent? Negative 1 minus 1. Negative 1 minus 1 is negative 2 for my final answer. We could write that using positive exponents, and we'll do more simplification as we go through this, but here at the very beginning we're not doing too much simplification. for my final answer. Take a moment. Any questions there? Any questions? The derivative of a number by itself is 0. The derivative of 3 was 0. Notice that last term just dropped off completely. Exponent times coefficient gives us the new coefficient. Subtract 1 to get the new exponent. Let's see, what about number 4? Oh, I think we can do this one right here on the paper. We have y equals x to the 11th. Y equals x to the 11th. Let's find, oh, notice they're using that dy dx notation for the derivative. I'll just still use y prime if it's okay with you. Y prime. We take the 11 and what do? If it's just a variable to a power, you move that power down, it becomes the coefficient. So an 11x to the, subtract 1, 11 minus 1 gives us the 10th power for a final answer. That's what you would type in there. Oh, let's see, surely we can, oh goodness. Okay, number 5. Look at number 5 right here. Oh, that writing's so small, let me recopy it now. Number 5. They give us h of t is equal to 7.6 minus 0.6t plus 1.2t cubed. And they want us to find h prime at t. So once again, they're asking us to do what? To find the derivative. So h prime at t. Okay, let's get started. The derivative of 7.6 is the derivative of a number without a variable attached to it is 0. Okay. Now the next term. The derivative of negative 6 times t. A number times the variable. Its derivative is just that number, so a minus 0.6. And the third term, what do? It's a number times a variable cubed. You take the 3 and multiply it by the 1.2, so that'll give us a plus 3.6. New exponent, t minus 1 gives me an exponent of 2. So we wouldn't want to type that 0 there, so our final answer, h prime of t is equal to negative 0.6 plus 3.6 t squared. Any questions there? So here for number 5, we have a negative 0.6 plus a 3.6 t squared that we would type into the blue box. Okay, now some good ones. Number 6. One thing I notice is the radical in the problem. You're going to have to get accustomed to the idea. When you run into a radical, from here on in, whether we're differentiating or when we're anti-differentiating, you're going to have to rewrite that using an exponent. So you're going to have to remember how to write radicals as exponents. Also, you're going to have to remember how to rewrite this. The only derivative rules we have now are for exponents is this power rule. You have to write that 3 divided by 8w to the 5th as a number times w to a power. That's the only thing we know how to differentiate at this point. So this is number 6. Let me write the problem down. Number 6. g of w is equal to 3 over 8w to the 5th plus 2 times the cube root of w. That's the function they want us to differentiate. We can't start differentiating that yet. We have to try to, we're going to have to try to get this written in a format in which we can apply the derivative rules. One thing you're going to have to remember is how to rewrite things using negative exponents. 3 divided by 8w to the 5th. This is not, I'm not differentiating yet. That's the same thing as 3/8. If you have something in the denominator and you want to move it out of the denominator, change the sign on the exponent. That's a w to the negative 5 power. So you're going to have to write that divided by, with the that denominator where the variable is. You're going to have to rewrite that fraction with the variable in the denominator using a negative exponent. That's what I'm trying to say. That cube root of w, you're going to have to rewrite that as w to the power. How can I rewrite a cube root using an exponent? What exponent is equivalent to a cube root? Yes, 1/3. You might want to remember your I'll state these are not derivative rules, what I'm writing here, okay? So the square root of b is the same thing as b to the 1/2. We'll be working with a lot of square roots this semester, and when we're differentiating square roots, the first thing we'll do is write it using an exponent of 1/2, and in general, the nth root of b, that's the same thing as b to the 1/n. And when people tell me this class is so hard, what I've discovered is that what they're really saying is that the algebraic manipulations are so hard. What I just did has nothing to do with the calculus part of this problem. What I just did at this point is just use algebra to rewrite each term as a number times a variable to a power, number times a variable to a power. That's not the calculus part of this problem. Now we're going to start the calculus portion of the problem. G prime of w. We're now going to start the calculus portion. You take the -5 and multiply it by what? By the 3/8. So you have -5 times 3/8 w. What do you do to get your new exponent? You subtract 1, -5 minus 1. I'll simplify that in a moment. Plus, now I'm going to do the next term. You take the 1/3 times the 2, 1/3 times 2, w. What do you do to the exponent? 1/3 minus 1 to get the new exponent. So now we'll go through cleaning all this up. G prime of w. -5 times 3/8. That's negative. Remember how you multiply an integer by a fraction? That's a -15/8 w. What's the new exponent? -5 minus 1 is a -6 plus 1/3 times 2, that's 2/3. Subtract 1/3 minus 1, what's that new exponent there? A -2/3. 1/3 minus 3/3, 1/3 minus 3/3 gives me the -2/3 for my final answer. Notice 15/8 can't be simplified, 2/3 can't be simplified, so I'll stop right there. Any questions? Uh-oh. Okay, let's see if I can find another one. Let's see. I guess we'll just continue on with number 7. Okay. Here, okay, number 7 right here. Let me I'm going to go to another. This is number 7. Oh, by the way, I didn't write in the answer for number 6 right there. It's on that scratch paper, so that's good enough for our purposes. We are doing, they give us f of x equals, oh, it's an easy one again. No radicals, no fractions. This one's pretty easy. There's number 7. Okay. What's the derivative of f of x equals 6x squared minus 5x plus 2? F prime of x is equal to 2 times 6, that's a 12. X to the what power? 2 minus 1 is an x to the first power, so I'll just write it as 12x. What's the derivative of negative 5x? A number times x, its derivative is just that number. The derivative of a number by itself, 0. So 12x minus 5, I feel bad if I don't write that answer there. So there. And I guess, what was the answer for number 6? I'm going to go ahead and write it in here. So, what is it? Negative 15/8 w to the negative 6 plus 2/3 w to the negative 2/3. That was the answer for number 6. And number 8. Okay, number 8. They want us to find the derivative of, let me do this, there. Number 8, y equals x cubed minus 16x squared plus 64x plus 5. At least there's no fractions and no radicals. You don't have to rewrite anything. You're ready to start finding the derivative. So you tell me, what's the derivative of the first term? The derivative of x cubed, I agree, that's going to be a 3x squared. What's the derivative of negative 16x squared? Okay, 2 times negative 16, that's a negative 32, x to the first power. What about the derivative of positive 64x? The derivative just a number times x, it's that number. And the derivative of 5? Okay, I agree with 0. For our final answer, a 3x squared minus 32x plus 64. For my final answer. Any questions there? You're going to need to get familiar with, not get familiar, you're going to have to commit these derivative rules to memory. We'll be using them all semester long. Also in terms of properties of exponents, you're going to have to remember how to write radicals. A square root is written as an exponent of 1/2. An nth root is written as an exponent of 1 over n. But that's not a derivative rule. That's just a definition of rational exponent, if you want to call it. So I'm going to take a break right now and let y'all absorb everything we've said so far. So I'll continue this discussion on derivatives sometime later. Bye-bye.